So all of this about enthalpy changes might lead you wondering how we actually measure this. So strap in, this presentation is all about how we find that value experimentally. Well, to do so requires an understanding of this basic principle. The system involves all of the chemicals involved in your reaction. So if it was neutralisation, it would be the acid and the alkali, or if it was a combustion, it would be everything involved. Now, this system has got the chemical energy stored within it, and it's going to either give that energy out into the surroundings or take energy from the surroundings when the reaction happens. Now, we measure the temperature change of the surroundings, which means when the surroundings get warmer, it means that the system has lost energy. And that is why enthalpy changes will be negative in exothermic reactions. What we know is that the total energy in the universe stays the same. So the energy change that increases the temperature of the surroundings must be equal to the energy released when the bonds broke or formed in the system itself. So if we wanted to measure the enthalpy change, we need to measure a temperature change. Now, the temperature change could be from any temperature to any other temperature. It's not specific. It's not particular to one particular temperature. So we don't use capital T to represent temperature in this instance. We use theta. And that difference between this temperature and that temperature, delta theta. In the equation that gives the amount of heat that has gone into, for example here, some water that has been heated up by a paraffin burner, well, the heat that's gone in is equal to mc delta theta, where m is the mass of the water that has been heated up, and C is the specific heat capacity of water. Now remember that what specific heat capacity represents is the amount of energy required to raise 1 gram by 1 degrees C, and of course this change in temperature. And this will enable us to calculate in kilojoules just how much heat has left those chemicals when there was that chemical reaction. Now we ultimately want to know the amount of energy per mole of reactant, in this case the per mole of paraffin that has been burned. So what we need to do is we need to work out how many moles of paraffin have been burned in the time interval over which we took the measurement. That requires us to measure the mass of the paraffin burner before and after the experiment. The difference is the sample mass, or the amount of paraffin that has physically burned. Dividing this by the molar mass of paraffin gives us the number of moles of paraffin. And then finally we need to divide the total amount of heat, Q, by the number of moles, and this will give us the enthalpy change. So let's take a look at this example. We've got a methanol burner, and what we know is some information about the fuel. That's the first thing we're going to look at. We measured the mass of the spirit burner and the methanol before and after, and we found there was a 3.2 gram usage of methanol. So that's how much fuel has burned. And so because the molar mass of methanol is 32, 3.2 grams being burnt means that we have burnt 0.1 mole. Isn't that convenient? Right, on to the next step. Let's take a look at the water. So what about that water, eh? Well, it'd be really nice if they just told us the mass of it, but they rarely will, because what they would want to do is for us to do a calculation that involved the density. It's much more likely that we would measure the volume of the water, not its mass. And so with the volume of the water and the density of water, we can work out how much mass it had. Volume divided by density will give you the mass. And so there we go, 300 divided by 1 equals 300 grams, no surprises there. So now we would put this into the heat equation, Q equals mc delta theta, to have 300 times 4.18 times 41. And so we get an amount of energy input into that water of 51.414 kilojoules. The final step, the one in which we can work out the enthalpy change of combustion of methanol, is that we need to recognise that here we only burnt 0.1 moles of methanol and transferred 51.414 kilojoules. We really need to know how much energy 1 mole would transfer. So the way in which we do this is we divide 51.414 by 0.1, and this gives us the ratio. And so it ends up being that per mole, 514.14 kilojoules of energy are released, which means the enthalpy change of combustion for methanol is minus 514.14 kilojoules per mole. Minus, of course, because it's exothermic. We are measuring a temperature rise in the environment. It means that the chemicals themselves have lost this much energy. Now, the true value, which is minus 726 kilojoules per mole, is a little bit different to this. And it may be different because maybe we haven't measured all of the heat, maybe there was incomplete combustion, evaporation from the wick, or maybe it was non-standard conditions. Also, what might happen is we might actually be experiencing cooling, that the actual water might actively be losing heat to the environment as quickly or at some rate whilst it is still being heated up. It would be important to draw a cooling curve and extrapolate it to work out what the total energy difference would have been. For more on that, it's worth watching the video of PAG 3.1. That shows exactly how to do this. If you were to try to find the enthalpy change of a reaction, any reaction, then what you could just do is mix the chemicals together and measure the temperature rise. It would be the same as the enthalpy change of neutralisation. All of these are just types of reaction, and they either give out or take in energy, and we can measure it just by measuring the temperature change. And what we do is we put it in a polystyrene cup, which insulates it from the environment. And what we would do is take measurements of the amounts of reactants. This would give us the amount of moles that have reacted, and we would then measure that temperature change. So here's an example. If we have the water going from 295 to 333, we have a temperature difference of 38 Kelvin. We're given the density and the specific heat capacity again, and we want to know what the energy change is. So the mass can be found as 50 grams. Now here's the thing, be careful. So this was an excess of zinc is added to 50 centimetres cubed of copper sulfate. Great, that means we know there's only about 50 grams of liquid there. But if we had two liquids like HCl and NaOH and it was 25 ml of both, we have 50 grams in total. You've got to consider what is the total mass of reactants that are heating up as a consequence of the reaction happening. So insert this mass into Q equals mc delta theta, and we get 7.942 kilojoules. Then we need to work out how many moles were involved. So we need to look. There was 0.05 moles of the copper sulfate involved in this reaction, and so therefore what we can do is calculate the enthalpy change at formation as the heat difference minus 7.942 divided by 0.05 is minus 159 kilojoules per mole. Again negative because again this is an exothermic reaction and the temperature of the surroundings went up.